Good afternoon, and welcome to our February Lunch with the Libraries, 3D Printing in Book Conservation with Senior Book Conservator Alessandro Scola. Thank you all for joining us. I'm Erin Czakowski, Senior Associate Director of Lifelong Learning with the Office of Alumni Relations at Johns Hopkins University. This ongoing series, Lunch with the Libraries, is made possible through partnerships with the Sheridan Libraries and University Museums, the Friends of Johns Hopkins University Libraries, and the Office of Alumni Relations Lifelong Learning. Following the presentation by our guest speaker, I encourage you to ask questions in the Q&A located at the bottom of the screen. We will do our best to respond to as many questions as we can in the time that is available. It is now my pleasure to introduce Claire Miller, President of Friends of the Libraries.
Thank you so much, Erin, and welcome everyone. On behalf of the Friends of the Johns Hopkins University Libraries, we are pleased to have you join us today for our monthly Lunch with the Libraries. This is our speaker series, which highlights the unique collections, pioneering initiatives, and outstanding staff, a bit of what you will see today. And thank you so much for the Johns Hopkins University Office of Alumni Relations, Lifelong Learning for your partnership in bringing this series to each and every one of you. We would love to have you join us as the Friends. We were formed in 1941, one of the oldest organizations like this in the country, and we are focused on financial support, advocacy, and events like this one to highlight all of the amazing things that the libraries bring to Johns Hopkins University. And now I have the great pleasure of introducing our speaker today, Alessandro Scola. He is the Senior Book Conservator at the Department of Conservation and Preservation of the Sheridan Libraries and Museums. He trained in Italy as the Center for Formazione Professionals in Cremona, and in a different private and public conservation labs in Italy and Spain. He worked as a private conservator in Treviglio, Italy for a few years, and then joined the University of Ulster in Northern Ireland for a 4-year book conservation preservation project as a conservation technician. He's been in the US since 2012, and he worked as a contractor in New York City, interned in Washington, D.C. at the Folger Shakespeare Library before joining Johns Hopkins University's Libraries and Museums in late 2013. He has been a staff member here since 2014. Please welcome Alessandro. It's going to be a great presentation.
So, hello, everybody. Happy Friday to everybody. Thank you, Claire, for your nice presentation. I have a lot of stuff to show you, so I would just jump into it immediately. So 3D printing in book conservation. My presentation will be divided roughly in 2 parts. The first one will be a general overview of what 3D printing is. The second part will focus on some applications of the 3D printing here in our lab, in our conservation lab. So first of all, what's a 3D printing? 3D printing is a manufacturing technique. It will be better, we should call it additive manufacturing. In general, we have 3 manufacturing techniques. The formative one, where the object is shaped in a mold or by passing through a die, and the process is governed by heat or pressure. This technique has a very high upfront investment, but then it's very cost effective when for mass production items, like 100,000 items, this is still the preferred manufacturing technique. Then we have the subtractive manufacturing technique, the CNC machining, turning, drilling, With this technique, the object is shaped by removing material from a solid starting block called a blank with drilling or cutting tools. This technique is best suited for low-mid production volumes, especially for metal parts. Unfortunately, it has a high volumes of waste materials. On the industrial setting, part of this material is recycled, but still, it's kind of a wasteful technique. Finally, we have the additive manufacture technique, or 3D printing, where the object is formed by adding material layer by layer. It's best suited for low volumes production or rapid prototyping, because it's actually a very slow process, I have to say. In general, it produces parts with lower physical and mechanical properties compared with other manufacturing techniques. Accuracy and repeatability might also be an issue. When we talk about 3D printing technology and materials, it's actually 3D printing. 3D printing is an umbrella term consisting of many different technologies like material extrusion, where thermoplastic are melted and dispensed through a nozzle. The technologies are called fused filament fabrication, or FFF, or fused deposition modeling, FDM. This technique uses mostly thermoplastics. It's probably the most common type of 3D printing on the market. You can find a machine for a few $100s. So it's a good way to start into the 3D printing world. Then we have vat polymerization that actually use a liquid photopolymer, a thermoset, in a vat that is selectively cured by light activated polymerization. There are two main techniques in this category: stereolithography, SLA, or direct light processing, DLP. This technique uses thermosets and not thermoplastic. Then we have powder bed fusion technique. With thermal energy, it selectively fuses the regions of a powder bed. If the material to be used is thermoplastic, the technique is called selective laser sintering, SLS. If the material is actually metal, the techniques are called direct metal laser sintering, DMLS, or selective laser melting, SLM, or electron beam melting, EBM. Then we have the other two techniques: material jetting, where droplets of materials are selectively deposited cured by UV light in a build plate. And we have material jetting, MJ, or drop on demand, DOD. Finally, binder jetting, where a liquid bonding agent selectively binds the regions of a powder bed. It's called binder jet, BJ. And this technique is used for sand, ceramics, and metals. This might be confusing. I'm gonna show you some videos that will demonstrate this technique. We'll show you more details about that. So focusing on a fused filament fabrication technique, which is the most common, which is the one we have in our lab. The variety of materials that can be used is huge. This is a typical scheme of what materials can be used, and it goes from commodity materials like a PLA or ABS to high performance like PEEK or PEI. The table on the right summarizes the difference between the extremes, let's say. So polylactic acid is a bioplastic, actually, derived from fermented plant starch, such as corn, cassava, sugarcane, or sugar beet pulp. It's a very low printing temperature, 200 degrees Celsius, more or less. And it doesn't need any other particular, it doesn't need to be, the building bed doesn't need to be heated. The chamber doesn't need to be heated either. So it's very simple to print. On the other extreme, we have a polyether ether ketone, PEEK, which has a printing temperature of almost 400 degrees, around 400 degrees Celsius, and is much more finicky to print. You can tell all those technical specification. They're very precise. As a consequence, the cost of these materials are incredibly different. And the PLA, you can buy a kilogram of it for 20 bucks. While for PEEK, the same amount, 1 kilogram, can cost you around $700. And the price of the machines that can handle those high-end materials are also very high. But now you can find thermoplastic embedded with wood dust or metal dust or ferromagnetic materials. So you can really go crazy about material to use for 3D printing. It's kind of fascinating. This is a machine that we actually have in our lab. It's the Ultimaker S5 Pro bundle. It consists of 3 main parts: air manager at the top, the actual printer in the middle, and the material station at the bottom. So the air manager contains an EPA filter, which can catch up to 95% of ultrafine particles. It's very important because regardless of the plastic used during the process, all plastic emits fumes when heated. So it's very important to filter them. It's actually very important to have an enclosure, so they all stay inside the printer. To be very careful, I usually tend to print during the night, so nobody's in the lab anyway, just to maximize the safety of the process. But that's definitely a good feature to have in your machine. The material station at the bottom is also very important because thermoplastic can be hygroscopic, so they can change property depending on the water content in the air. So the material station keeps all material the same dry, the same humidity levels, the optimum humidity levels, I should say. It's also great because pretty much all the materials included into the station can be loaded into the printer automatically. So I don't need to manually select the plastic and then feed the printer. It's all done automatically, which is great. It's still interesting that it's not random. The helmet glue at the bottom left corner, I actually use it all the time. Although it is almost $10,000 machine, still they recommend to use this $2 glue stick to increase the adhesion of the first layer of your print, and to also ease the removal of your print from the bed. I thought it was interesting because it's still, yeah. This machine is great because there's an onboard camera. It's connected to the network, so I can remote control it. And often, I start the print from home. If I know the print is 12 hours long, maybe the night before I just started, and the day after I show up in the lab and the print is done, which is a great feature. And the onboard camera allows me to control the print and see if something is failing, there's a problem. That's great. Our printer is a dependent dual extrusion system, which means that we can use 2 materials at the same time. You've seen the green box at the top right. It can be the same material, 2 colors of the same materials or 2 different materials, which obviously expand the range of design that we can print with this machine. And also has the swappable print cores, which means the print cores or hot hands is where the plastic goes through, is melted and comes out and deposited on the bed. They're all different because they have all different sized nozzles. Some of them are specific for some kind of materials, more abrasive ones, for example, like carbon fiber reinforced plastics. So this machine is great because it allows me to change very easily those hot hands or print cores, as Ultimakers calls them, and depending on the materials or the structure or the design I want to print. This is another diagram of our machine, which is a Bowden extrusion system, which simply means that the filament of plastic is fed into the extruder, which is motorized and pushes the plastic through the Bowden tubes into the hot end, where the plastic is melted and then deposited on the building plate. The direct extrusion system are a little bit different machines where the extruder is attached to the hot end and moves with it. I'm not going into details here because, yeah, we'll take another presentation, I guess. So now we'll switch to a playlist of short videos I prepared. They will show you how those different techniques work. And so this is a close-up of a FFF machine working. You need to imagine that that filament is actually 0.4 millimeter wide. I believe this shot was made with an endoscope attached to the hot end of the machine. This is preparing for printing. So it's going, it's printing first the walls, the object. And now it started to print the first layer, which is very important for the stability of the whole object. This is when the second layer starts on top of the first. Again, it starts from the walls first. And that will fill the gap between the walls. The second video is a time lapse of a very big build. Kind of amazing. They don't say how long it took them to print this, but I will guess a few days overall. Looking at this model, I don't think you can achieve the same results with any of the other technique, manufacturing technique at a decent price, let's say. The next video is another very popular fused filament fabrication machine. It's called the Delta machines. And it's interesting because the hot end is at the center, is connected to these arms, and the movements on the X, Y, and Z axis are all depending on the vertical movements on those rods on the sides. The next one, it's an example of SLA.
3D models layer by layer. Among them is SLA. SLA stands for stereolithography, a 3D printing process that uses a UV laser to cure liquid resin into hardened plastic. Upside down or inverted stereolithography is the most common SLA system. Depending on the machine, resin is either poured into a tank by a user or dispensed automatically from a cartridge. At the beginning of the print, a build platform is lowered into the resin, leaving only a thin layer of liquid in between the platform and the bottom of the tank. Galvanometers direct the UV laser through a transparent window at the bottom of the resin tank, drawing a cross-section of the 3D model and selectively hardening the material. The print is built in consecutive layers, each less than 100 microns thick. When a layer is complete, the part is peeled from the bottom of the tank, letting fresh resin flow beneath, and the platform is lowered once again. Originally developed in the 80s, SLA was confined to large industrial machines until recently. Today, desktop stereolithography offers affordable, high-resolution 3D printing that fits conveniently in your workspace. SLA allows for the use of a wide range of materials with diverse physical properties. Whether you're an engineer, product designer, sculptor, jeweler, or dentist, there's a material for your application.
The next one is about the selective laser sintering, which uses a powder material, in this case, a thermoplastic, deposited on as a thin layer on the bed. Then heat is applied to solidify it. When the first layer is done, the second layer of the powder is laid on top of it. And again, heat is applied to create the layer. As you can tell, it's a very laborious process because once the objects are printed, they need to be extracted by this big, the bucket, from the bucket. It's a very laborious process. You need to clean it. You need to use sandblaster or air blaster to remove all the residues. The results that can be obtained with these machines are incredible. I actually saw one of these machines live when I went to visit a supplier of 3D printing machines and materials, and it's kind of amazing what can they do, but you know, it's a big operation. Next is the metal laser sintering.
Direct metal laser sintering, also known as DMLS, is an additive manufacturing technology that creates metal parts directly from 3D CAD data without the need for tooling. DMLS utilizes a variety of metal and alloy materials, such as stainless steel, cobalt chrome, and Inconel, to create strong, durable parts and prototypes. DMLS is an excellent choice for functional metal prototypes, high-temperature applications, and end-use parts. The DMLS process begins in the same fashion as other layer additive manufacturing technologies. A program takes 3D CAD data and mathematically slices it into 2D cross-sections. Each of these sections will act as a blueprint, telling the DMLS machine exactly where to sinter the metal material. The data is then transferred to the DMLS equipment. A recoater assembly pushes powdered metal material from the powder supply to create a uniform layer over the base plate. A laser then draws a 2D cross-section on the surface of the build material, heating and fusing the material. Once a single layer is complete, the base plate is lowered just enough to make room for the next layer. More material is raised from the cartridge and recoated evenly upon the previously sintered layer. The DMLS machine continues to sinter layer upon layer, building from the bottom up. As the part is built, support structures are added to give supplemental strength to fine features and overhanging surfaces. The completed part is then removed from the base plate and treated with an age-hardening heat process to further harden the part. Any support structures are also removed at this time. With numerous surface treatment and hand polishing options available through service providers, DMLS parts can be used in highly cosmetic applications. Typical uses for DMLS include tools and manufacturing aids, small integrated structures, dental components, surgical implants, and aerospace parts.
This is a video from the Department of Defense. It's about how they use material jetting in a medical application.
Material jetting is another type of three-dimensional printing system which has a multitude of applications within the realm of military medicine. This process creates patient-specific anatomical models with a drop-on-demand method that incorporates materials of different colors, transparencies, and flexibilities into the build. After the operator sends the object to the printer from a standalone computer system, the printheads begin to apply the photopolymer material. This light-activated resin is jetted, sprayed, or extruded horizontally along the X and Y axis onto the build surface. Meanwhile, high-intensity ultraviolet lights cure the layer, allowing the polymer to quickly transition from liquid to solid. In order to integrate special features, several different materials are mixed together during the build to obtain new substances consisting of all various hues, opacities, or even hardness. As the printing process continues, each new layer bonds to the previous one until the object is complete. A technician then removes the model from the build platform, and the temporary supports can be detached by hand through the use of a pressure washer or in a bath of basic solution. Once all the supports are eliminated, any transparent items are coated with resin or another transparent material, then polished by hand. Next, the models are allowed to cure or set. This ensures the final product achieves optimal visualization properties. Because material jetting can accommodate multiple materials within an individual build, it's an extremely useful printer at the 3D Medical Applications Center. Technicians incorporate distinct external and internal anatomy, such as metal hardware, teeth roots, and tumors. These features provide a visual reference which aid medical personnel in pre-fitting devices for both routine and highly complex surgical procedures.
Binder jetting additive manufacturing is a process inspired by the technology of inkjet printers. In this process, a liquid binder is selectively deposited on a powder bed with a printhead. It is a growing process that allows the production of parts for the manufacturing, medical, and dental industries. This technique enables the production of metallic and ceramic parts as well as sand molds for castings. To start the process, a 3D drawing is imported into the printer software. The powder to be used is placed in a dispenser, which ensures a constant supply during printing. First, a powder layer of a specific thickness is spread. Thereafter, the printing head, moving on two axes, projects the binder where necessary. Before moving on to the next layer, the solvent contained in the binder is evaporated by an incandescent lamp. The powder bed is then lowered and a new powder layer is deposited. Therefore, the production takes place in a series of steps that build the part layer by layer. When the cycle is completed, the binder is cured by placing the container in a furnace. The temperature and time depend on the type of binder employed during printing. After this step, unbound particles are removed to reveal the part or the mold. After this step, the sand molds are ready to be used in foundries. The metal and ceramic parts must undergo sintering, infiltration, heat treatment, or hot isostatic pressing before being used.
Okay, now I'm going to show you a few videos about the materials, different materials, other than plastic or metal that can be used for 3D printing. The first one is clay. second one is about building components for a house. So with these very components, they're actually building an entire.
We're very excited for this partnership.
In the Coachella Valley.
The first of its kind in the world. We're building 15 homes that are 3D printed and fully sustainable.
We're getting a better product. We're getting a product that's more controlled, and we're able to accomplish this at the same time with sustainability at the forefront.
Mighty Buildings has the most sophisticated product on the market.
All right, the last video of this series, kind of the
A
weirdest one.
juicy, sizzling steak made by computer. While obtaining regular meat is a process that's been taking place for millennia, cow, butcher, beef, Redefined Meat, a meat alternative startup out of Israel, makes their product using a highly technical process. The mix of soy and pea protein, chickpeas, beetroot, nutritional yeast, and coconut fat is formed into steak-like shapes using a 3D printer.
Our goal.
Honestly, I'm not sure about this application of 3D printing, but hey, some of the things is worth it. I'm going back to my presentation. Okay, now briefly about the process of the workflow involved with 3D printing. First, you design your model. I use Autodesk Fusion 360, which is a parametric modeling software, which I love, but it's not the only one. There are many other options out there. Then you need to import your 3D modeling into a slicing software, which creates the layers that will be printed and also produces the G code that will tell the machine where to move in space. The third step is printing, and then there is assembly, which is manual, obviously. I left out the post-processing, which in some application is necessary. And with post-processing, I mean you can send your object after assembly or before assembly, or you can, for example, if you print with ABS, you can expose the object to acetone fumes to smooth out the surface. But I usually don't post-process my object, so I didn't include it in this slide. Now, when designing for 3D printing, you need to be aware of a few features. 3D printed objects are anisotropic, which means they do not behave in the same way in all directions. There are many studies about this. The diagrams on the right shows you how. If you apply tension in a direction perpendicular to the direction of the filament, you have a weaker object. It is much stronger otherwise if the filaments are parallel to the tension force applied. So you need to be aware of this when you decide how you print your object. Vertical, horizontal, along the x-axis, or y-axis. Those are all considerations that you have to figure out before starting printing. Another, also you need to pay attention to overhangs and bridges. So this is a typical example. If you want to print vertically Y, you might be fine if the overhanging parts are less than 45 degrees at an angle with the vertical. Otherwise, for example, the T, which is actually 99 degrees from the vertical, you need support structures because otherwise your printer will fail. When it comes to bridges, it depends on the length of the bridges. So small bridges, a few millimeters long, you might not need support. If they are like 1 inch or 2 inches long, you might need support. Again, it's something else you need to keep in mind while designing and then printing your object. Supports, if you have a machine with one hot hand, the supports are created with the same material of your object. And then they need to be manually removed, which can be a laborious process. Recently, there is another option. I'll show you another short video. Okay, this is a demonstration of using a soluble material to create the support that will be easily removed than in water. It's a PVA-based material. I've used it. It works pretty well. And this is used mostly for complicated structures. I should also say that it's a very expensive material, so I need to be careful in using it. But it works beautifully. So when your object is done, you put in a tank with water, and slowly the water will remove all the support structure. And you end up with your pretty complicated structure. It will be impossible to achieve otherwise. And now I go back to my presentation. All right, in general about 3D printing and the conservation world or museum world, I should say, the Image Permanence Institute carried out a survey last year. I participated in it. And they made the results available like a few weeks ago. It's very interesting. Please go to the website if you want more information. I just extrapolated some details that were interesting to me. Like, as you can tell, the adoption of 3D printing is relatively recent. We got our machine in 2020 or 2021, so the last few years. Most of the institutions use 3D printing material for printing plastic, which is not surprising, which is because printing metal, ceramic, or glass requires machines of a high cost. Sorry. So as you can tell, not many people are using 3D printing for actual integration or conservation work because it's very complicated. Mostly it's used for exhibition or display purposes. I'm not surprised about that. That's how I use a 3D printer for exhibition, for example. Longevity and safety of 3D printed materials is problematic because there is not much literature about it. And as you can tell, many institutions uses a 3D printed object without really assessing the materials, including myself. I didn't have the time or the tools to do it, which is problematic to a certain extent, but that's the reality for now. And clearly people are looking for new ways to new approaches to conservation and preservation. 3D printing allows you to create structure that would be otherwise impossible to create at a decent cost and easily. Okay, this is two short videos about the machines that we have in our lab, actually. And here I'm printing a prototype for a reading room cradle for books. This is a macro shot. That's the real speed of the machine. Not very fast, but it works fine. Sorry. This is the final product. It took a few prints to have all the components I needed. And then eventually I assembled this prototype, completely 3D printed. And the idea is to have a cradle that can be used for display or reading books flat, like in this case, or tilted at an angle. This is one of the most recent 3D printed object made in our lab. I tried to print a cradle, the whole cradle in one print, but it's too, the 3D print is too slow. I don't think this is the way to go. But I tried, it works if needed. Another approach would be create a modular system when you have a component that can be assembled depending on, for example, the tilting angle that you want to for your cradle. So then, for some of you might have visited the exhibit, the Women of the Book exhibit at GPL. Some of the mounts were actually 3D printed. For example, the mount for the triptych. You can see the components on the left. Or the frame for the ivory item. Or those little brackets for the shroud. They're all 3D printed. This is the rotating cradle. We wanted to show this binding, this precious binding, and rotate it so all sides could be visible. But I needed a special bracket to cover the motor. And so 3D printing was the only solution. Okay, this is another application. It's a laser measuring device. This is the second version of this prototype. The first version was actually used by Michael for measuring special collection items that were going to LSC. And according to him, it was incredibly fast, improved the efficiency and accuracy of the process incredibly. Basically, the idea was to create a jig and to attach a laser measuring device, that's this Leica. Instead of using a ruler to measure the book. You know, time is clicking, so I'm going a little bit fast now. And this is one of the last, again, 3D printed object. Is a prototype for a bookend for the new Stern Center Evergreen. The idea is to slide the bookend along this aluminum profile, which is attached to the bottom of the bookshelf. So you can position your bookend wherever you want along the shelf. Okay, I'll go very fast here. It's the major problem with 3D printing, I think, it's that it uses plastic, or at least the technology that we use. So use of plastic is a problem, especially in the US. Unfortunately, those numbers are kind of embarrassing, but that's a reality of plastic recycling in this country. There are ways to mitigate it, and we have tried to in our lab. For example, our display cradles, now we have a new system, which is modular. We can reuse several pieces. We have been using this system for the last several years, and we have reduced the use of new plastic by, I would say, 80% at least, even more probably. Another way would be to use some companies like TerraCycle. You fill those boxes with your plastic, you send it to them, and they will select them, they will repurpose them. This is what they use at the Huntington Library, for example. I would like to look into it a little bit closer and see if we can use it here. Precious Plastic is a project that started in 2013 in the Netherlands. And it's an open source project. They give you all the manuals, instruction to build machines that can recycle plastic. The shredder, for example, when you reduce the plastic in small pieces, or other machines to work with the recycled plastic. I have a video about this, but I don't think we'll have time to look at it. But please have a look at their website. It's a very interesting project. They're trying to do something. It's free open source project. So these are instead two companies that, again, sell machines that will allow you to somehow close the loop. They are similar. They have a shredder. When the plastic, your waste plastic is reduced in small pieces, and then they melt it and they create a new filament that you can use for your 3D printer. Or even better, now they're appearing some 3D printer that can use pellet plastic or flakes from recycled plastic directly, which means you can skip the filament production phase. And if you have a shredder in this machine, it will be easy to repurpose waste plastic. Obviously, I would love to have something like this in our lab or on the campus at least. It's overall, it will take like a $50,000 investment, but yeah, I don't know, maybe with the renovation of the library, it can do something. We'll see, this is a kind of a dream. I had a few more videos to show you, but I think time is running out, unfortunately. So again, for my voice, I'm a little bit sick again. I stopped sharing. Here we are.
Well, thank you, Alessandro, for a fantastic and thorough presentation. We are now moving into the Q&A portion of the program. I encourage you to ask questions in the Q&A located at the bottom of your screen. We already have some very great questions queued up here. And we do have about 8 minutes or so left, so we'll get to as many as we can in the time that is available. First question I was going to ask is, what is the cost of a 3D printed object?
If you print yourself, it can be a few dollars. Let's say designing the object might take a long time. I mean, it might take half an hour or hundreds of hours, depending on the object. But then a small object can be literally a few dollars. If you use an external company to print them, if you want one prototype, it's like a few $100. If you want 100 copies of the same object, it's again below $10. So it depends on the quantity, but it can be very cheap, generally speaking. Unless you use high-end plastics, in that case, it's more expensive, but generally it's very, very cheap.
Well, thank you. Next question. How is this technology being used by faculty and students for research and learning?
That's a good question. I can't really answer. I think we have a makerspace, Hopkins. But I'm not sure on campus. I mean, I would assume we have more 3D printing around, but I don't really know. I know the makerspace in Remington has a bunch of 3D printing, which are dedicated for students. So staff cannot use it, but students can. I'm sure they're using it. But unfortunately, I don't have details about this. I cannot.
Well, I mean, for right now, we're all learning exactly in this space. So it's fantastic. One thing though, you shared so many fantastic videos and your PowerPoint presentation as well. One viewer here was wondering if we could get links to the videos, you know, maybe in our follow-up email.
Yes, I can surely provide. I created a playlist and I can surely share it. No problem with that.
Wonderful. We have a question here from Beth. It says, in your book mounts, did you put any barrier like polyester or mylar between the object and the 3D printed cradle to keep the two from touching? Must be a very specific question.
Because of the temporality of the exhibit, I did it in a few occasions. I did for the triptych, Women on the Book, I put a layer of polypropylene film at the bottom, because unfortunately the shelf was kind of sticky. It was not allowed to off gas properly, to dry properly, so it was a little bit sticky. So in that case, I put a layer of polypropylene. But otherwise I didn't.
Interesting.
I kind of was confident and trusting the materials, but our exhibits are never too long, although more research is needed. It's what the survey of the Image Permanence Institute showed. We need more research and more investments to really figure out how to use 3D printing in its conservation of exhibits.
We have one question here from Elizabeth Long, who is asking, how did you learn how to do the 3D design for these objects? And do you share your designs with other libraries?
At the moment, no, because I'm not sharing them, because I'm kind of tweaking them still. I mean, probably it's a lifelong project, I don't know, but we keep changing little details. I want first to test them here at Hopkins for real. The last prototype is very promising. I'm very confident that I can create something that can be used actually by teachers or students here. So after that phase, if they work, then I will have no problem in sharing the design. How I learned it, when COVID hit, I was forced home. So what do? So some new technology, maybe it's time to learn something new. And 3D printing came to my mind. It was in my mind for a long time. COVID gave me the excuse to really get some books, get a $200 3D printer to put in my basement and start messing with it. Fusion 360 is a cumbersome software. Can be daunting, but surely as a steep learning curve. It's a fantastic software, and once you start using it, it's an addiction, honestly. If you like making things.
Absolutely.
Yeah.
And we have a lot of makers here, I think, asking questions because there's some more technical questions about how these things work. I'll share a few. One from Bill is, does the air handler allow you to have the printer located in the lab, or is it located in another area?
It's located in the lab, in the entrance of the lab. We mostly print with PLA, which supposedly gives away less hazardous fumes than other plastics. Still, it's in a contained space. Ventilation in our lab is okay. And as I said, I try to print mostly when nobody's around, just in case, mostly during the night. But yeah, the problem, I've seen many people printing with in their living room without any enclosure and filters. I'm not sure about that. The filter that we have, it's probably enough to limit the fumes by a lot.
Yeah, there is a question here about off-gassing. Like, how long do you let the objects off-gas?
That's a good question. Again, we need more research because nobody knows. I don't know. And those filaments, unfortunately, they are copyright. We don't know how they are made, honestly. It's PLA, but yeah, what's more than PLA in the materials? We don't know. So it's very difficult to establish that.
Mm-hmm.
Usually when we build something with PVA, for example, box with cardboard and PVA, we let it off gases for several weeks. We can. That would be great. For 3D printing, I would do the same. But yeah, there are no data. Unfortunately, I keep searching for information, and it's always kind of depressing. There's not much around there. Mm-hmm. Things are improving, yes, but still, we need more research into these materials.
So interesting. Well, I think we are now out of time, and we'd certainly like to thank you, Alessandro, for your presentation.
You're welcome.
It's been a pleasure. And I'd like to thank Claire for joining us also this afternoon, and for all of our attendees for joining us for this webinar. As Alessandro said, thank you for sharing the links to your videos. We'll include them in a follow-up email and a recording as well of the program, and an upcoming event schedule as well. So thank you again for joining us, and I hope everyone
has... If
yes?
somebody has any other questions, please send me an email. I'll be happy to answer it, no problem. If you want to visit the lab and see the machine operating, please shoot us an email.
We'll include that email in the follow-up. So thank you all for joining us. Have a wonderful weekend.
Okay, thank you.